Hi, folks. We're going to take a look at this question from today's lesson. So here we've got a company that's looking to lay cable between two subdivisions on opposite sides of a river. And they want us to minimize the cost of this work. Okay, and we see here that it's $40 to lay cable underground and $80 to lay cable underwater. So let's start by representing the situation with a diagram. So here I've got an east-west river. So I'll draw it this way. Okay, they tell us that the river is 100 meters wide. And I'm going from point A, which is on the north, point P, which is on the north side, to point Q, which is on the south side, but 1,200 meters down east. Okay, so there's Q, and it's 1,200 meters away to the east. Okay, and let's think about how this cable could be laid. So it could be partly underwater, partly underground. Now, in fact, if there was no conditions on the cost, the best way to lay it would be, of course, the line that joins the 2 points. But of course, that means it's fully underwater, which is the more expensive way. One way is to minimize the underwater portion, so go straight down and then do the rest on the land. But of course, that's going to give us the longest cable. Or it could be somewhere in between. So what I want to try to do when I draw a scenario, I want to try to avoid these sort of special circumstances like the ones I just talked about. So what I'm going to do is I'm going to draw a portion across the river like this, and then another portion here on the land. Okay, and I'll represent W, the length underwater, and I'll represent L, the portion that's on land. All right. So if we want to determine the total cost, so we're going to take the cost underwater multiplied by the length, since it's given per meter, and then I can do the same thing with the part under land. Okay, so the cost is equal to, well, if I take the part underwater, that's $80 per meter times the number of meters underwater plus $40 times the number of meters underground. All right, now we have the usual scenario that we've got two variables in our equation. So we have to find a way to connect these two variables. All right. So I'm going to look back on this diagram, and something we've seen now a few times that you might see in this diagram is that if I draw a line across the river, I see that I've created a right angle triangle. Okay, where this side here is equal to 100. This side here is just the length underwater. So I'm going to need to work with this side of the triangle. So at first glance, I look at this and I say, well, this side here can be written as 1,200 minus L, okay, which would be perfectly fine, except that means that I'm going to have a 1,200 minus L inside the Pythagoras equation, and that's going to be pretty annoying. So a little trick that we use is the portion that involves Pythagoras is, let's actually call this some other variable, x. Okay, so here now, L can now be written as 1,200 minus x. Sorry about that. And then W, I can relate to x by using Pythagoras. So I have x squared plus 100 squared is equal to W squared. Okay? So instead of writing one variable in terms of the other, I'm writing both variables L and W in terms of this third variable x. So now I can take this and input it into my equation. Now, of course, I'm going to have to solve for W here. So here there's no way to get out of having a square root. So W is just going to be equal to the square root of x squared plus 100 squared. All right, so let's input everything into our equation. So here we have 80 times this expression here that we just found, x squared plus 100 squared, and then plus 40 times 1,200 minus x. And this is, not too much simplifying I can do here. And so here I'm going to ask myself, well, what are the parameters on x? Well, I see x at the very least can be equal to 0. So if x is equal to 0, it means I've come straight down along the water and then along the edge, the whole 1,200 meters, or at most, x would be 1,200. So that means this here would go straight to Q, and that would be my x. So here x has to be greater than or equal to 0 and less than or equal to 1,200. So I see here that I am working on a closed interval. Okay, so now we'll do the calculus portion here. So I'll take the derivative. So 80 is just a constant. So here we have, think of this as to the 1/2. So here we have 1/2 x squared plus 100 squared all to the negative 1/2. Okay, and then times the derivative of this inside portion, which is just going to be 2x. And then here we have the derivative of the 40 is just a constant, and the derivative of 1,200 minus x. Well, that's just equal to -1. Okay, and so now I'm going to set this equal to 0. So 0 is equal to, so I see the 2's cancel out here. So I have 80x all over the square root of x squared plus 100 squared. Okay, and then minus 40. So in order to solve this, I'm just going to multiply both sides of the equation by this square root to get it out of the denominator. So here that's just 0. So 0 equals 80x minus 40 times square root of x squared plus 100 squared. Okay, now this might look like an issue because I've got this x here and then I've got this x squared that is stuck inside the square root. But what I'm just going to do is I'm just going to bring this to the other side of the equation. I'm going to write it this way. I have 80x equals 40 times the square root of x squared plus 100 squared. And now I can just square both sides, which is going to allow me to get rid of the square root. So here I've got 80 squared. That's going to be 6,400 x squared equals 40 squared is going to be 1,600 times, well, the square of the square root just gets rid of the square root, x squared plus 100 squared. Okay. So here, distribute this, bring this over to the other side. So let's just check here what's, should be able to do this in my head, but just to be sure, let's do 6,400 minus 1,600, and that gives us 4,800 x squared equals 1,600 times 100 squared. I'm not going to bother multiplying that because I'm going to put everything into my calculator. So 1,600 times 100 squared. Okay, and now let's solve for x. So here, this is going to be plus or minus the square root of 1,600 times 100 squared all over 4,800. Okay, of course, I'm not interested in the negative value. Okay, since x is a measure of length, and so now let's stick this into our calculator. So we've got 1,600 times 100 squared. Oops, sorry, let's do that squared. There we go. Divided by 4,800. Okay, and then I'm going to take that to the exponent of 0.5 because that's what taking the square root is. So here, where do we have that? That's square root 0.5. And so here we have 57.7 approximately. All right, so this is the x value, which is going to be my critical point. So the question is, what's going to give me my lowest cost? So instead of testing my interval, which I really don't feel like doing with this ugly function, I'm just going to use the fact that this is a closed interval. Okay, so what I'm going to do is I'm going to test my cost at 0, my cost at 1,200, and my cost at 57.7. Okay, so let's go here and let's put in the cost when x is equal to 0. Okay, so here 0 plus 100 squared, square root of 100 squared is 100, so I have 80 times 100, okay, plus 40 times, well, if x is equal to 0, this is just 1200, okay, 40 times 1200. And so the cost here is $56,000. Okay, let's check now with 1200. Okay, so I see that this part here is just going to go to 0. Okay, so here we have 1200 squared plus 100 squared equals, take that to the exponent of 1/2 because that's what square root is. Okay, and times 80 is equal to 96,333. So clearly this is not the way to go. And so the last one here is 57.7, and this one I will have to do all the parts of it. So here, let's try to do this really carefully. So 80, whoops, let's start again. 80 times, okay, so that's 57.7 squared plus 100 squared, okay, and that's all to the exponent of 0.5, okay, and then plus 40 times 1200 minus 57.7, and we get 54,928. So here, 54,928. And so that is the lowest of the three. All right. So now let's actually answer the question. And the question is, determine the least expensive way to lay the required cable. Okay. So what I'm going to do is I'm going to specify how much of it is by water and how much of it is by land. Okay. So for my answer here, so the part by land is going to be 1200 minus the x value, which minimizes it, which was 57.7. So that's 1200 minus 57.7. Okay, so we have 1142.3 meters, and then the width is just going to be equal to the square root of 57.7 squared plus 100 squared. Okay, so we're seeing here that most of it is along land with a small portion, much smaller portion along the water. So this is going to be 57.7 squared plus 100 squared, and then all to the 0.5, which takes the square root, and that's 115 we'll say 115.5. Okay, and there we have it. So let's do a recap here. So step number 1 was to draw an accurate diagram and to represent the scenario not with one of these special scenarios, which means not right across from P to Q and not straight down and across, but represent something in between. From there, we saw that we could use a right angle triangle again, and in this case here, use the fact that Pythagoras applies. Okay, we saved ourselves a little bit of time by, instead of working with L and W, working with this third variable x, which allowed me to find an expression for L and find an expression for W in a fairly easy way. Unfortunately, we weren't able to avoid a square root, so I had to be careful when we take our derivative. And again, don't forget that when we solve this derivative, we use this trick of bringing the values for x on one side and the values of the square root on the other side, so we could square both sides and get rid of the square root. And because we were working on a closed interval, in order to determine the minimum value, I just tested the two endpoints and my one critical point, and we found that the critical point is the one that generated the smallest value, which is what we were looking for. And the last thing was to answer the question that was being asked, which was how we would accomplish this. So we determined the length along the land and the length underwater. Okay, that is it for this one.